The dot product. The dot product is a way of multiplying two vectors where the answer is a scalar. The dot product of a vector A with a vector B is simply the sum of the products of the corresponding components of A and B. So notice that it is the first component multiplied by the first component plus the second component multiplied by the second component plus the third component multiplied by the third component. And the notation is A dot B. The dot product of two vectors is a real number, not a vector, so it is a scalar. And for this reason, the dot product is often called the scalar product, or sometimes we also call it the inner product. So dot product, scalar product, and inner product all refer to the same thing. And in two dimensions, it is a similar definition, except that we only have two components to multiply. So in the example here, we are going to take the dot product of these two-dimensional vectors. So to do this, we're going to take the component 2 and multiply it to the component 3, plus the component positive 4 multiplied by negative 1. And this is 6 plus negative 4, which is equal to 2. For the next one, it's the same idea, except that now we have vectors in 3 dimensions. So we will multiply the corresponding components together, and then we will add them up. So we get negative 1 times 6 plus positive 7 times 2 plus 4 times negative 1/2. And this is negative 6 plus 14 minus 2, which is equal to 6. And finally, we can also take the dot product when we have vectors using I, j, and k. It works the same. We're going to take the first component here, which is the number 1, multiplied with the first component over here. Notice that you don't see an I, so that means the component is 0. So that's going to be 1 times 0. Plus, then we take the second component here multiplied with the second component, so that's 2 times 2. And finally, the third component multiplied by the third component, which is negative 3 times negative 1. And if you do the math here, you get 4 plus 3, which is equal to 7. So the dot product is a very simple product to compute, and it turns out to be very useful as well. First, let's talk about some properties of the dot product. So if we have 3 vectors, A, B, and C, and these are all 3-dimensional vectors, and then C here is a scalar, we have the following. A vector dotted with itself, so the dot product of a vector with itself, is the magnitude of that vector squared. Dot product is also commutative, so A dot B is the same as B dot A. And we have a distributive property with the dot product. So the vector A dot product with the vector B plus C is the same as the dot product of A and B and the dot product of A and C, and then added together. Here, a scalar multiple of A dot product with V is the same as the dot product of A and B multiplied by the scalar, or you could multiply B by the scalar and then take the dot product with A. All of these are equal. And finally, the dot product of any vector with the 0 vector is always 0. Now, out of all of these, I think I will prove this first one for you. So if you think of the vector A as being the vector A1, A2, A3, we know that the magnitude of vector A is simply the square root of A1 squared plus A2 squared plus A3 squared. And the dot product of the vector A with itself, we know is the vector A1, A2, A3, dot product with itself, A1, A2, A3. And the definition of the dot product tells us we are going to take A1 times A1 plus A2 times A2 plus A3 times A3. And this, of course, is A1 squared plus A2 squared plus A3 squared. And notice that that is pretty much what we have right here, except that the magnitude of A also has the square root. So this is equal to the square root of A1 squared plus A2 squared plus A3 squared, quantity squared. And that, of course, is the magnitude of A, quantity squared. And you can prove any of these by simply showing that the left-hand side is the same as the right-hand side. All you would have to do is define vectors A, B, and C the same way that I have defined vector A here, and then just show that the two sides are equal. Next, we have a theorem involving the dot product. So if theta is the angle between two vectors A and B, so theta is the angle here between those two vectors, then it is true that the dot product of A and B is equal to the magnitude of A times the magnitude of B times the cosine of theta. I'm not going to prove this theorem. You could always look at the proof in a textbook, but basically this comes from the law of cosines. So if you remember the law of cosines, you can prove this by using that law. So as an example, if the vectors A and B have lengths 4 and 6, and the angle between them is pi over 3, find the dot product of A and B. So we know from the previous page that the dot product of A and B is equal to the magnitude of A multiplied by the magnitude of B times the cosine of the angle theta between A and B. Now, we know that vector A has a length of 4, so that would be the magnitude of A, multiplied by vector B has a length of 6, multiplied by the cosine of the angle between the vectors, which they tell us is pi over 3. And so this would simply be 24 multiplied by 1/2, which is equal to 12. So we can compute the dot product in this case, even though we don't know the components of these vectors, because of the theorem on the previous page. Notice that if we come back to this theorem here, and if we divide both sides by the magnitude of A and the magnitude of B, we will have vector A dot product with vector B divided by the magnitude of A times the magnitude of B is equal to cosine of theta. Right? So if we just divide both sides by this, we get a new formula which tells us how to find the angle between two vectors. So here is a clean version of that theorem, which is called a corollary because this is basically a theorem that follows very simply from another theorem. Also, if two vectors A and B are orthogonal, that only happens if the dot product is 0. And orthogonal means perpendicular. So just think of orthogonal as a fancy word for perpendicular. We don't normally say two vectors are perpendicular. We say they are orthogonal to each other. Now, why is that true? Why is it that if the dot product is 0, they are orthogonal? Well, it's very simple. If the dot product of two vectors is 0, then that would mean that this quantity here is 0. And that would mean the cosine of theta would be equal to 0. And this only happens when theta is 90 degrees, right? And it's true the other way around as well. So if theta is 90 degrees, then we know that cosine of theta would be 0, and therefore the dot product would have to be 0. So the dot product being 0 is a quick and easy way to check to see that two vectors are perpendicular to each other. We can further classify vectors. We can say that the vector A and B have an angle between them that is acute if the dot product is positive. And we can say the vector A and B has an angle between them that is obtuse if the dot product is negative. And then, of course, right in the middle of acute and obtuse is when they have a right angle, and that is when the dot product is equal to 0. So in the next example, we want to find the angle between the vectors A and B given here. So to do this, we need to compute the dot product of A and B. So to do that dot product, we are going to multiply 2 times 5, which is 10, plus 2 times negative 3, which is negative 6, plus negative 1 times 2, which is negative 2. And this dot product equals 2. We also need the magnitude of vector A, which is going to be the square root of 2 squared plus 2 squared plus 1, which is the square root of 9, or 3. And the magnitude of B is equal to the square root of 5 squared plus negative 3 squared plus 2 squared, which is the square root of 25 plus 9 plus 4, which is the square root of 38. And now we know that cosine of the angle between A and B is equal to the dot product of A and B divided by the magnitude of A multiplied by the magnitude of B, which is equal to 2 divided by 3 times the square root of 38. And of course, we can solve for theta by taking the inverse cosine of both sides. And this is approximately 1.46 radians, or 84 degrees. Next, we want to show that the following vectors here are perpendicular to each other. To do this, we simply need to show that the dot product is 0. So if I call this vector A and I call this vector B, the dot product of A and B is going to be 2 multiplied by 5, which is 10, plus 2 multiplied by negative 4, which is negative 8, and negative 1 multiplied by 2, which is negative 2, and you will notice that this dot product is 0, which means these vectors are perpendicular to each other. Now suppose we have two vectors A and B as pictured here, and they have the angle theta between the two vectors. If I shine a light perpendicular to vector A, you can see the vector B would make a shadow on vector A. The length of this shadow is what we call the component projection of B onto A. And to find that length, all I would need to do is solve for that side of the triangle. So if I call that x, we know the cosine of theta is equal to x divided by the magnitude of B, right? Because we know cosine is the adjacent side over the hypotenuse. And that means that x would be equal to the magnitude of B times the cosine of theta. But we also know that the cosine of theta is equal to the dot product of A and B divided by the magnitude of A times the magnitude of B. So I can substitute this into here, and we get that component projection is the magnitude of B multiplied by the dot product of A and B divided by the magnitude of A times the magnitude of B, And finally, the magnitude of b here cancels out, and we get the formula you see there, which is the component projection of b onto A is equal to the dot product of A and B divided by the magnitude of A. Now, suppose we're having the same scenario here, a light shining down, making a shadow here. But now, instead of thinking of this as simply a length, let's think of this as a vector. What would this vector be? Well, we know the length of that vector is right here. That's what we just found. So to get this vector, all we have to do is take the unit vector pointing in the same direction as A and multiply it by this length. So this is what we call the projection of vector B onto vector A. And it is going to be the length of that shadow, which is the dot product of A and B divided by the magnitude of A, multiplied by the unit vector that points in the same direction as A, which is the vector A divided by the magnitude of A. And we can write this as the dot product of A and B divided by the magnitude of A squared multiplied by vector A. And this is what we call the projection of B onto A. So just to summarize, we have the component projection of B onto A, also known as the scalar projection. That's where we're just looking for the length of this thing. And then we have the vector projection of B onto A. Let's do an example. So in this example, we want to find the scalar projection and the vector projection of the vector B given here onto the vector A given here. So the scalar projection, also known as the component projection of B onto A, is equal to, the formula says it's the dot product of A and B divided by the magnitude of vector A. And so we got to compute the dot product. Let's go ahead and do that here. Dot product of A and B here is going to be negative 2 times 1, which is negative 2, plus 3 times 1, which is 3, plus 1 times 2, which is 2, and this is equal to 3. Divided by the magnitude of vector A, let's go ahead and figure that out. The magnitude of vector A is the square root of negative 2 squared plus 3 squared plus 1 squared, which is the square root of 4 plus 9 plus 1, which is the square root of 14. Now, you could simplify this, I suppose, and you could say this is 3 radical 14 over 14. So that is the scalar projection of B onto A. Now, to find the vector projection of B onto A, we use the formula dot product of A and B divided by the magnitude of A squared, and then multiplied by the vector A. Now, we don't have to redo all the work here. We already know the dot product is 3. We already know the magnitude of vector A is the square root of 14. Now we are going to square that, and then we're going to multiply that by the vector A, which is negative 2, 3, and 1. So this is 3/14 multiplied by the vector negative 2, 3, and 1. And if I distribute that, we are going to get 3/14 times negative 2, which is negative 3/7. 3/14 times 3, which is positive 9 over 14. And finally, 3/14 times 1, which is 3/14. And this is the vector projection of B onto A. And that concludes this video lesson.